Hello and welcome to our final section of astronomy about life in the universe. To kick things off, we're looking at a lake in California that's filled with these strange microorganisms that actually thrive off of arsenic in their composition. And this is just to represent the wide variety of materials that living organisms can incorporate and use in order to survive and thrive. You know what it is, and it's time for our last reading quiz of astronomy. This is going to sound strange, but we're not going to ask what sounds like an astronomy question, but more of a biology question. It's that, why is carbon so good for making life forms? What about carbon makes it so important to be designated for use in life in our organic matter? So for the last time, go ahead and pause the video. Come right back when you have an answer in mind. So the primary property about carbon is its ability to bond into long chains. And this is going to be very important for us as we're going to build up how we go from simple atoms up to complex organisms. Now, I imagine a lot of you would say, why is carbon favorable? Because it is organic. And that's just a definition. We just say, hey, organic matter are things that are built out of carbon. So most of us, when we talk about life in astronomy, obviously your heads are going to jump straight to ET. And we'll get there. We'll talk about our search for ET. But we're going to build up. We're actually talking about the importance, the significance of life in the universe. And we'll start off from just a physics or chemical perspective on what is life. What does it mean to have DNA? What does that do? And building up from there, we'll ask, what meets the definition of life? And how do we build life out of what starts off as seemingly simple chains of molecules? There we'll start to branch out into astrobiology, start to get the bigger and bigger picture on life in this universe. And finally, we'll discuss our search for the extraterrestrials. As a motivator, why discuss life in a astronomy course? Well, one part of it is that life is a product of the universe. If you want to be a bit more philosophical about it, you can say that, hey, us, human beings, we are a part of the universe that have reached a level of consciousness that we're trying to understand the universe. Phrased in another way, we are the universe trying to understand itself. And understanding the universe is also trying to understand life. So with that in mind, one theme that we'll have in this lecture is that we're going to describe life as just a growing complex chemical process. And we'll say that life actually arose out of primordial soup of organic molecules. We'll build up to there. Now, some teaser, let's look at this rock. This is a meteorite found in the Antarctica. And by doing some analysis, they were able to figure out that this meteorite was probably a Martian rock, literally a chunk of Mars that got smashed into, thrown off through space, and luckily managed to crash here on Earth. And what scientists did was that they scanned this thing, probed it, to create this picture. This is created using an electron scanning microscope. And in it, they found patterns like this. Patterns that remind us of microbial life. So, a big open-ended question is, hey, is this fossilized microorganisms from Mars? There is no consensus on this. This could just be minerals, and our eyes are just looking for the organisms that we want to find. But it could be a microorganism. And this is one aspect of our understanding of life on a bigger astronomical scale that will come back later in this video series. Let's get into some of the chemistry of life, and all of our discussion is going to apply to what we'll say is terrestrial life. Now, for all we know, there is only terrestrial life out there, but I think it's important to make the emphasis when necessary. Coming around on terrestrial life, all of us are primarily composed of 6 elements: carbon, hydrogen, oxygen, nitrogen, and then trace amounts of phosphorus and sulfur. And for example of that, here we're looking at vitamin B12. And you can see all of those, plus there's a little bit of the phosphorus that we talked about. So these are the main elements that compose any living organism on this earth. We say that carbon is a building block for life. In fact, we literally define organic compounds to be any chemical that's just primarily composed of carbon. So what about carbon that makes it so important? It's this tetravalent nature of it. Another way to say it, if you have your chemistry goggles back in mind, is that it has 4 valence electrons. Basically, carbon is a really great job of sharing up to 4 electrons with other elements. And because of that, you're able to form these long chains. Here's a really simple one. Say we have some methane, some CH4, so carbon with 4 hydrogen atoms bonded to it. And you can imagine I could make a series of chemical reactions where I could just split this bond with this hydrogen atom and just stitch something else on there, glue another piece there. So I break this bond, free up that hydrogen, and put in this other molecule in there, and I'll have now acetylcyanide, C3H3NO. And look at this. Here's a carbon, 1, 2, 3, 4 bonds. That goes to another carbon, 1, 2, 3, 4. And to another carbon, 1, 2, 3, 4. And that's what I mean by tetravalent. These carbons do a great job of making 4 bonds and creates this long chain series. This is the relatively simple molecule here that we've represented. So upgrading that, let's look at just allotropes of carbon. Every picture you see here is just carbon atoms bonded with carbon atoms. And look at all these unique, fascinating shapes. My favorite, graphene here. So these are carbon atoms arranged in nice little sheets. So if you're taking notes right now of your pencil, and not using a pen, it has to be a pencil here now. When you're taking notes, literally what you're doing is scratching off a layer of this graphite. You're scratching off one. So then you take another writing utensil, you make your another stroke with your pencil, and another layer of carbon has been stripped off from your pencil and deposited onto your paper. And so on and so forth until you need to sharpen your pencil. So that's how your pencil, the graphite on your pencil, from the carbon in there, gets deposited on your paper. Then we find other shapes of carbon that's useful. Diamond, we always think about diamond and its wonderful, miraculous properties in bending light and what we'd call a nice, pretty image. We also find other absolutely fascinating examples of this, to the Buckminster fullerene, which is a 60 carbon atoms combined in this spherical, almost soccer ball shape. One of my personal favorites is the carbon nanotubes. Just carbon bonded in a way that makes these unique, long, tubular shapes. And this stuff, by some definitions of stress and strain, can be stronger than steel, but you can thread with it. There are very fascinating macroscopic properties. All of this carbon material that have different structural shapes. And that's emphasis here. That's very much the emphasis here, that the form determines the function. And you're going to hear me say that multiple times throughout this video. To cap this all off, I do think it's worth mentioning what we call organosilicone ideas. Look at the periodic table. Here you have carbon, and directly underneath it is silicone. So that silicone, like carbon, has a tetravalent nature. You can make long, complex chains of silicone atoms. And so it's been postulated that there could be a silicone-based life forms out there. Hence the Star Trek reference on the right side here, where Captain Kirk is fighting a silicone life form. Emphasis here is that if you can make long, complex chains, you can make big, complex molecules, and that will build up to organisms like ourselves. And that in the universe, while on Earth, carbon is the basis for life. All known life is carbon-based. That's not to rule out the possibility of more exotic creatures somewhere out there in the cosmos.